We'll see if that works. There we go. Okay. So that was line 3. Line 3 is our N. Executions, line 4 would be, we have the same thing. We have K equals 1. That happens one time. K less than N times, since we started K off at 1. And then N minus 1 for the number of times K plus plus gets hit. Right, which could be a little bit misleading if N were 0, because that'd be -1. So we'd have to account for that. Otherwise, N minus 1 for the body. And then line 6 is 2. All right, so line 2 is 2n plus 2 for to ask about the different lines. All right, there's a +1 and a -1, so this one would just be 2n, for example. All right, if the question would ask what's the total cost, and we just take all that and add it all together. That would be our total cost, and our big O is going to be n. All right, because our fastest growing term that we have anywhere in here is our n's, and it's going to be the sum multiplication of those n's, right? It's going to be like 5n in total or whatever this is. But when we transform it from functional notation to big O, that coefficient will disappear. Okay. Just drop that screenshot in the Discord. Test channel. And we can carry on. Okay, our singly linked lists. All right, whenever we're adding a node into a list, first step is to create the node. All right, so we just go ahead and drop a box in there to represent our node. One part will be our data. And then one part will be our link. So whatever it is, we'll just go ahead and set those as best we can. The wrapping wasn't quite ideal. Second step, link it into the existing list. If the list is empty, then the node is the list. All right, so there are several places where we might add a new node into the existing list. Either end is a likely destination. We also have the middle as an option. If we're looking to maintain data order. All right, so adding to the front of the list. So if we already have an existing list of data points. All right, let's say we have 5 as a data point, and we had 22 as another data point. and this being our exciting list. I'll just call that first node, first node. And we want to go ahead and add 19. So this is our newly added node. And we want to fold in to our existing structure. All right, so new node is going to have our link member that we want to set. To our first node as things are named here. All right, so say new node link equals first. That's going to cause that link to form. And then next step, to make that new node the beginning of our list, first equals our new node. And that just moves first from where it was to represent our new first node, right? And our new chain is just one longer than it was before. And just redrawing our list. New node, just a temporary named node. So I will not carry that name over because that's going to be out of scope. What is the arrow? That's the arrow syntax for dereferencing the pointer, right? So new node would be a pointer. All right, let me go ahead and add up. Nodes there, new node. New node passing along 19. And that does our first step does the job of creating our box. All right, so I can label that as step 1. All right, so step 1. Pencil, okay. All right, step 1. Create the box. Step 2. Link that new box to our existing list. And then step 3, bring the first on over to our new node. Right, so new node is a pointer type. We use the arrow syntax in C++ to dereference the pointer and expose the members that we want to work with. And then in this particular code base, link is what we're calling our self-referential pointer type. That's nice and small. Let's expand that a little bit. All right, we can do the same thing. Adding to the end of the list. Generally, when we have adding to the end of the list pattern, we're going to want to increase our number of named nodes here. Right now, if we're only maintaining a first pointer, we could do this. We can iterate down our list, get to this node 22, and then link that to our newly created node. But that's a linear solution to a problem that can be done in constant time. So what we'll do, if we want to support adding to the other end of the list, we'll add another named pointer called last to the list type. So we can go ahead and link our newly created node. All right, so this time we'll go and add, oh, what's good number 9. All right, so we'll create our new node with 9. Let's make it 7. I haven't used that character before. Let's make it 7. And what we want is we want this new node to come up after our last node. And we want to link it to the last node. So it's going to be very similar as before. This time we don't need to set the link pointer. This will just say as a 0, it doesn't go anywhere. All right, so 0 just represents the null pointer. Other ways we might represent a null pointer when drawing it is an arrow that points down. If I can get this arrow to point down, that'll work. All right, so 0 is a null pointer, just points nowhere. All right, so the first step, still pretty much the same thing as we had when adding to the beginning of the list. Yeah, first and last and head and tail would be synonymous, just different names for the same thing. Does linked list have a limit how many nodes we can add? Nope. You're just constrained by however much heap space the operating system will allow your application to take. So as long as you can create in the nodes, you can go ahead and keep on linking them to the existing list. All right, so we'll go ahead and remove step 2 here. And we'll say last link points to our new node. All right, so this is setting up our link for our last node to point to our new node. And then one more step to shift down. Last equals new node, that moves our last pointer down to the end of the list. Right, so after we complete the operation, the very first node, whatever data point it holds, is at one extreme, and our very last node is at the opposite extreme. If we want to go ahead and add in more data points either at the beginning or at the end, it's pretty much the same 3 lines of code, just working with slightly different fields. Create the node, link the node, and then adjust the first if we're adding to the beginning, or adjust the last if we're adding to the end. Then we'll have the reverse operation of removing the front. Okay. First, or head, and removing from the back. All right, okay, last, or tail. All right, various names for calling same ideas. It's just a named pointer to one of the nodes in the list. All right, so this time we are not creating a node, but rather we're going to cause a data point to be removed. So let's remove from the left side, calling first here. All right, so we do want to grab the data. So that we can go ahead and send that data back. Usually if someone's going to be pulling something out of the list, it's because they're consuming that information and it's being used up by whatever we're doing. Because in C++, we're responsible for maintaining trash collection ourselves. We do want a temp pointer to track the node so that we can go ahead and delete that later on. Next, we're going to go ahead and slide the first pointer down. All right, so by saying first equals first link, that's going to cause this to slide down. And then point at node 5. All right, so first, now over here, node 5, after we do operation 3, first equals first link. First link is the value inside this pointer, which is the same as the memory address of our node. So by saying first equals first link, now first holds onto the memory address of where this node is in memory. After that has shifted down, we can go ahead and clean up memory by deleting temp. All right, that will cause this node to cease to exist. So I'll go ahead and copy the whole thing. So that can be expunged, given back to the heap. And we can send the data back to whoever's calling us. All right, you add to a list that has 3 elements. Now you have 4. If you delete from a list that has 4 elements, now you go down to 3. All right, and the same code works so long as there is a list to delete from. First can keep on going until first is set equal to the last pointer, which is just going to be null. Causing the list to be destroyed. Now, here we're a little bit stuck. We're moving from the right side, which is not well supported by a singly linked list. All right, we can't just say delete last sort of thing. All right, if we were trying to come in here and just delete the node, oops. Get my boxes in order here. Try to get them in order. All right, there we go. Right, if we just try to run ahead and delete last, right, just kill this box. We end up here with a little dangling pointer, right? This pointer was pointing to a location in memory where that box used to exist. And as the application keeps running, at some point in time, this box will likely become something else. We also have the issue of this pointer was not nulled out as it should be. The last node should represent the last box in our list. As the last box in our list, we want last to be here and this pointer to be null. So we have to do a little bit of work. We need to get a temp pointer and iterate to the node that is just before last. All right, so we will create, yes.
So is the node arrow point to the link, is that like iterating with .next in Python?
Yeah, so we'll just say temp equal to first, and while temp next is not equal to last, we can just have it just slide down here, right? We'll look at the actual code.
Okay, so the link is how you iterate in C++?
With a linked lists, the way you work your way through the list is with the pointers that link to the next to the next node in the list, right? It's typically called next if in a singly linked list. A doubly linked list, next and previous we are common naming, but they're just variable names, right? So the names can be arbitrary.
Okay, so next is a thing in C++.
Next is just the name of the pointer, so it's not a keyword. So it's nothing to do with C++. Right? You do what? Right? You could call it A if you wanted to, or Z.
Mhm.
It's
Okay,
just what
thank you.
we're, yeah, because it's our user defined data type, node type. Now, if we're working with a library, they're going to have their name for it. And then we'd be forced to use whatever their name is. All right, so the first step is we need to get our temp pointer in position. So temp will point to our 22 node. All right, so we'll get that done with just a loop. All right. We'll probably be grabbing the data, right? And data equals last data. This part can happen in a couple places. We want to null out this pointer so we don't have a dangling pointer. Temp link, as we're calling it here, equals null or 0, whatever we're using. All right, so that causes this link to not point to the node anymore. We need to give the memory back to avoid a memory leak. We're going to be doing lots of things in here that can easily lead to a memory leak. If we can't get to an object that's dynamically allocated anymore, that's the foundation of a memory leak. So right now, if we were to skip line 4 and then just move on to line 5 and set our last equal to over here, right? We've just run out of ways to get to this node, right? So skipping line 4, we had 2 ways of getting to this node. We had this pointer on temp that was pointing there, and we had last directly pointing to this node. So before we get to 0 pointers referring to this object, we need to delete it so that we don't have a memory leak. Right, so yeah, delete tells the heap that that memory is now available. Often it may or may not memset it, right? Those are details we're not concerned with as far as the structure is concerned, because as far as the structure is concerned, that node is no longer part of its little universe. Right, so this scenario, all right, so deleting from the right required us to loop from the left to just before the last element. So if there are 10 items in the list, then we have 9 iterations. If there are 100 elements, then there are 99. And so on, giving us a linear rate of growth, or big O n. Right, so in the general sense, as much as possible, when the objective is only dealing with a single data point, we want to have big O notations that are closer in magnitude to big O1 than big O n. All right, so depending on the problem, we might be able to do that, or we might not. It just depends on our solution, what we're doing, and all that, given context of what's going on. Okay. Now let's apply this. And let's see. All right, so as a quick reminder, stack is abstract data type. It specifies operations, not the implementation of those operations, as well as what the big O should be for those operations. All right, so with our stack, we have push. Just going to add data to the top. We go 1. And we have pop, which is going to remove data from the top, which is also big O 1. So our push pattern, all right, create the node, link that node to the top node, make that node the top. All right, those are our basic steps. And then pop, it's gonna be similar. You have data cleanup to do here, or memory cleanup. Top data. And we'll have to create our temp node. Temp node for memory cleanup. And then we can go ahead and slide the top over. Slide the top down. All right, clean memory. And then return our data. Let's see, so I wrote some code here earlier. This is my array base. Never mind, getting ahead of myself. Any questions about our fundamental operations here for the stack, pushing and popping data? All right, let's go grab some code. And files, linear structures, int single link list. Probably already had it downloaded, so version 2 or 3, whatever. 4. Oh, so many times download the same code file. And go ahead and get Visual Studio here and step through some code. Right, so we saw this briefly last time. The node class is like my drawings. We have just 2 fields or members inside the definition. One represents whatever the data is. Right, if you want to use templates instead of int, feel free. Any reason left to right? Just left to right's way English characters are represented, right? Words go from left to right, so we're just doing that arbitrarily, right? We could do up, down, left, right, forwards, backwards, getting closer to the screen, further away from the screen. The links are just pointing to where they are in memory, and where they are in memory is quite arbitrary. In fact, if you were to inspect memory addresses, the third node might have a lower memory address than the second node, and the fourth node might have a higher memory address than the first node. It just depends on where the heap decided to give us space for the allocation. Right, overloaded constructor. If we don't specify our next pointer, it will be set to null by default. So we can create a node with just data, or we can create a node by passing an already existing pointer, and we'll use that memory address to set our next pointer. All right, so our list class and SSL list are two named pointers, which we're calling head and tail. Constructor is just setting the null. You always make sure you think set to null. All right, C++, when you call the new keyword, it generally mem sets everything to 0 for you already, but different environments might behave differently. So it's always good to be explicit instead of relying on implicit behavior, just to get ahead of potential bugs when you're trying to take your code to a different platform or a different language. Excuse me. The deconstructor, we'll talk about that one later still, is empty, right? If the list has no elements in it, right, we don't have a count field in this type, so we're just relying on the head state. Initially, head is 0, right? So initially we have an empty list, so the head is null. So it returns back whether or not it's empty. And our add to head. All right, so we saw this again last time. Hopefully you've been poking at it a little bit to see what's going on here. So our very first time we come in, the head is null. So we go ahead and create our box with data, and head is 0. So we will go ahead and create that box. Right, our next pointer will be set to 0. So we have our box. The data is 5, 10, 15, whatever the data point was, and it's not pointing anywhere. Our next pointer points to 0. The new keyword then returns back, we're in memory, the box was allocated, and says that's our head. Right. Second time we call this. Right, so we had our box with 5. Let's see. All right, drawing here, right? So first time along. Right, we had our 22 node we created, that was the head. Then we come along and create 5. Create our box, passing in 5, and then their existing head. That causes 5 to link to 22. And that box comes back, and we assign that to head. That causes the head to now move over to 5. Come in here one other time, this time creating 19. All right, 5 is the current head of the list. Create the box with 19. We pass 19 in here to the constructor of our node type. It links it, all right, it sets our link to our existing node 5, and then changes the head. All right, so breaking the code down here. And on tests, you do need to break the code down here because you cannot rely on code that you cannot see. All right, so my sample code here has an overloaded constructor. You can't assume that type of code when taking the test. Yeah, so for this one, head is tracking the left side and tail is tracking the right side. So only when the list is empty do we do anything with our tail pointer. Right, since this is our add to head function. If the list is empty, when tail is null, we just set the tail and head. So tail and head are equivalent in 2 scenarios. When the list is empty, they're both null. So head and tail are equal to each other. And when the list has one element in it, the head and the tail are the same node. So if we had just the 22 node, this would be the head, this would be the tail. As nodes are added either in front of 22 or after 22, then head and tail will diverge. If we delete down to one node, then they will converge back together. Or if we destroy the list entirely such that it is empty, they both go back to null. All right, adding to tail, two scenarios. Here the code does need a branch. If it is an empty list, we create the node. That node is the head, that node is the tail, with whatever data point we create it with. Otherwise, we have a non-empty list. Tail's not null indicates a non-empty list. We'll go ahead and create the node. So first step, then link that node to our existing tail. And then we slide the tail over. Tail equals tail next. Just like we had here before. So 22 was our tail, which we called last over here. Right, we create the node. We set the next equal to the node, and then we set it over. Right. So here I have the steps broken out as 3 steps. These steps are step 1, creating the node, step 2, linking the node, and step 3, sliding the node down the list. Delete from head. Note that this function has a precondition. If the list is empty, head is null. Dereferencing a null pointer is a failure at runtime. Cannot dereference something that does not exist. Cannot follow a pointer to a location in memory if that location in memory is null. So keep that in mind that delete from head does have a precondition that the list is not empty. So before calling this, you should check to see if the list is empty. Otherwise, deleting from the head will fail with a runtime exception. But we're grabbing our data and a temporary variable, so we can go ahead and clean up that temporary variable later. We have 2 other cases that we're going to consider when head is equal to tail. I mentioned earlier there's 2 circumstances when this is the case. One, when the list is empty, which we won't get there. We will not get to line 140. The list is empty because we already blew up on line 137. The second case is when there is a single node in the list. If we have a single node in the list, deleting from the head does need to worry about the tail because it needs to set that to null, as well as setting the head to null to represent an empty list. Yeah, so we're first, last, left, right, or whatever we want to call the pointers. A little bit arbitrary. There are some conventions, but the key thing is they represent opposite ends of the list. Okay, since this particular class is a little more generic in its purpose, it's not specifically for a stack, it's not specifically for a queue or specifically for another data structure. They're just being called head and tail. Since your head as a human is at the top of your body, when we want to take this code and transform it to a stack-based implementation, we will take head and rename it as top and then lose the tail altogether because the stack doesn't care about it. If we want to take this code and then translate it into a queue implementation, right, typically we see the queue as the front of the line and the back of the line. So we'll take head and name it front, and we'll take tail and name it back to represent the ends of the list. All right, so our first branch here, we're going from a 1-element list to a 0-element list. Head and tail are both null. Otherwise, we have 2 or more nodes, and the head's just going to slide over 1. Right, like we had here before. First was originally over here 19. First slides down to the next node, which is just 5, whoever's after it. And we send the data on back. All right, and delete from tail, as I mentioned earlier. We have our unfortunate loop here. This one also has the same precondition. Attempting to dereference a null pointer will fail. So if the list is not empty, line 152 will explode. Yeah, so in this code here, the head will take us to the tail. Then the tail will take us nowhere. The tail pointer is just a shortcut to that end of that list. Okay. Line 153, this is our scenario when we have a single node list. Single node list, when we're deleting from the tail, means we have to deal with the head because we need to set that to null. All right, memory cleanup, head and tail are null. Now we have an empty list. Otherwise, temp pointer that needs to iterate down. Notice this lovely semicolon, a common bug that new developers like to have on their headers, like the if headers, putting a semicolon, or a class header, put a semicolon where it shouldn't be there. Here it's okay because we actually have an empty loop. All the work is being done right here. Temp is just sliding down. Temp equals temp next. Temp equals temp next. This is the work. This is the state change that's happening here. We just keep on moving down until we get to the point where temp next is the tail. Right? This condition is keeping us one before the last node, right? Because we want temp to be one before the end, before we break our linkage to the end here, before that node that was existing before. All right, 7 before 7 gets taken away from our list. So when we get to this point, temp is now pointing to a predecessor. We can delete the tail. And we can go ahead and slide the tail over one to the left and then set the next pointer so that it's not dangling, pointing to something it shouldn't be before. It's very important to make sure pointers are set to null because we often have tests looking to see if the value is null. Because that's one of the other ways we know that we've hit the end of the list. If the next pointer of the node that we're at is null, then there are no more nodes beyond us, and we're at the end of the list. Right? So here we have two ways, since we have a named pointer called tail that tells us that. All right, delete node. This covers all the scenarios: deleting from the head, deleting from the tail, or deleting from somewhere in the middle. All right, so the deleting from the somewhere in the middle case involves bridging the gap. All right, so you just check out this code when you get around to it. Let's say we want to delete from the middle. Grab this one. Reset. Okay, so let's say we want to delete 22. All right, so our final state will have 5 pointing to 7. Temp is here just to help us along. We need someone to iterate down. That's going to track the node just to the left of the node that we want to get rid of, which we can call predecessor. I think I called it pred over here in the code. All right, pred, that's short for predecessor. It's whoever's to the left of the node that we want to kill, and then we'll have temp. As the node that we want to delete. All right, so this one wants to bridge the gap. And there's a few ways we can write the code to do that. But one way, predecessor sets its next pointer to temp's next pointer. All right, and then we can go ahead and delete the temp. All right, so take 5. We have 5. Come all the way over here and point to temp next. All right, so we've jumped over it. And after we've jumped over it, we can go ahead and clear out that node. All right, and our list is as we want it to be, with 22 no longer part of the equation. The reverse would be adding a node into the gap, which we wouldn't do with this type of data, nor would we delete with this type of data, because deleting from the middle in an unordered set is very arbitrary. There's no generally needed or practical reason to do that, because it's in the middle and we really have little idea what's in the middle. But I mean, you can always come up with a scenario where you want to do it. You have a queue and someone wants to get out of the line, right? So you have to find wherever they are and then remove them from the line. It's just an uncommon use case. When we do the reverse, we're going to take our node, find where we want to put it. All right, so we want to add 44. Do the same things before. Pointer to the left of where we want the data. Then bridge it in. All right, so we'll start with a similar state here. All right, so we're going to be creating our box with 44, just like we do when adding to the front or the back. And we want to bridge it in. So when we're doing this, we're creating our new node. Our new node does not have state for its pointer. All right, the default state for a new node's next pointer is null. So when we're setting pointers, your general rule of thumb is the ones that you want to manipulate first are the ones that are null. If we try to manipulate 5's next pointer first, we lose track of 7. Right? Last happens to be 7 right now, but this could have been a couple dozen nodes between here and last. So we need to make sure we don't lose track of anybody as we are bridging our gap. So once 44 is successfully linked to 7, now we have someone that knows how to get there. And we can go ahead and readjust 5's pointer to point to 44, and then we have bridged our gap. Again, we'd want to use this for ordered data. Okay. So our stacks and queues, this code base can be used for either a stack or a queue, right? So it has extra pieces. A stack does not need a tail. And stack does not need adding to tail, right? Or deleting from tail, right? Push is add to head and pop is delete from head, right? Because stack just operates on one end of the list. If we were to take this foundation and turn it into a queue class, then adding to the head becomes irrelevant, and deleting from the tail becomes relevant, because when we're adding in a queue, within queue, we're always adding to the end of the list, and when we're pulling data with a DQ, we're always pulling from the front of the list, right? So there are very similar patterns between these two data structures. It's just a matter of where they want to work on their data. Pop Pop is removing from the top of the stack. All right, so pop's purely a stack operation. So with a linked list, it's removing from whatever is considered to be the top of the list. And in the case of a linked list, we would just have the one node. So there's only one place to do the operation, because a stack does not care at all about the tail. It is superfluous information. Let's see. All right, array-based stacks. Array-based stacks, still the same idea as link-based stacks, but instead of using pointers to link us through a series of nodes, we're just going to use an array, all right, our instar array here. And constructor specifies the capacity. It's defaulting to 0, so it's a completely empty stack. For in case you need it to be a completely empty stack, it'd be a little bit useless because I don't have any code here. That allows you to resize the stack, and that's stack 2.0. All right, a couple of helper functions that give you a little bit of details or metadata about the type, right? However big it was sized as, so you know how big it is. And so the outside knows how big it is, plus we'll use this with our push to make sure we don't overflow our stack, because that's always a bad idea. Otherwise, push and pop are our operations that we care about. And where's our code? Right, so, all right, just like we saw leave last time briefly, pushing and popping, constant time operations. And we just have an edge case here so we don't overflow our array. And we just set our data point in there, working on the top, and pop, same idea, just working at the top end of our stack to get our data back out. Later on tonight, I will dig in this a little bit. Did I forget to move my test code? No, that's the wrong one. There's my test code. Give you some direction on testing code, right? Because the keyboard is a terrible interface layer to test code. So I'll swing back to this one a little bit later tonight. Any general questions about stacks or stack implementations at the moment?
Actually, yeah, I just have a question about like some of the syntax that you just did. Yeah. So you're for the array top plus plus, you're incrementing the top value and
Yep.
then adding, okay. And then you're decrementing the top value when you return it.
Right. Yeah.
Is that because it's pointing to always to like one element above the stack?
Yeah. So the top, right? So our initial state for our top is 0. And the stack is empty. Right.
Yeah.
So there's nothing on the stack. So it's one above, if you want to view it that way. And there's different ways. There's implementations where we can set this to be -1. And there's a bug here, mind you, for this, which I'm going to get to later tonight. Right. So there's two ways of doing it. The top could be looking at the value at the top, in which case -1 would be the way you want to implement that, which means you prefix increment top. So top goes to where it needs to be. Right. So that's just an implementation specific detail where there's you can cut it from the right side, or you want to cut your apple in half, you can cut it from the right to cut it in half, or you can cut it from the left to cut it in half. Either way, you get the apple cut in half. It's just a matter of the timing to make sure that you got the blade at the halfway point for when you start to cut. All right, so top starts off at 0. Since this is a postfix increment, At index 0, we will set our data point, right? So if we push 5, 5 will go to index 0, and then the top will be set to 1. So the top at this point in time does point to the next place that we would add data to. So when we pop, since the current top is not pointing at a data element, we need to use a prefix syntax to decrement first before grabbing the value out of the array.
Okay, I understand that. So like if it'd be like plus plus top, basically we'd be pushing at 1. Like the first data would be at 1 instead of 0.
Right, yeah. So if we had this as a prefix, then we would not be utilizing the first element if we don't change what top's initial value is.
Okay, thank you.
Okay, let's see. Right, so for queues, similar idea here, except if we were to transform this to a queue, we need to keep track of two things, right? In front and back, because it cares about both ends. And our push and pop do get a little bit more complicated because with a stack, the top is growing and shrinking at one end with no wasted space at the bottom. The bottom's just the oldest value and it sticks around there until we pop all the way back down to it. With our queue, what we need to do is get into the concept of a circular array. So let's get a dot going on that. All right, so a circular array is just an array where the first element is after the last element. So we're wrapping around. We get to the right boundary of the array such that we're back to the beginning. Right, you'll typically see this with round robin schedulers, schedulers, where we keep just rotating through the jobs, one after the other. So let's get a small table here. Index, job, whatever, paint job. We've got a backup job, and we've got whatever our main engine trying to do all its fun work. All right, so the job scheduler runs the paint job, period of time, then swaps to the backup job. For a period of time, then moves on to the engine job for a period of time, before coming back to the paint job. And keeps on this trend. All right, so basically the current job index equals 0. Painting right now, then we'll go ahead and slide it over Job index moves over to backup. And the engine, before we get back to painting. All right, so it just keeps on looping back around. So when we try to go beyond, right, so as in our code somewhere, wherever, we could say, move next type thing, and job index plus, and if job index are equal our array size, just move it back around, job index equals 0. Right? Or alternatively, job index module equals size type thing. Just divide job index, get the remainder, and this forces, right? Module is very, very useful operator for keeping us within the boundary of our array. So that makes the array circular. An array-based implementation for a queue will need to rely on a circular array. As the front to the end of the array needs to reset back to 0. And the same also applies to the back index. It also needs to reset. All right, so let's look at some queue states. And that's pretty good enough. And we got our state and index. State 0, right? So we're empty. Empty array. State 1, we go ahead and enqueue 5. All right, so let's go ahead and say we're going to enqueue 5, enqueue 8, enqueue 1, and then we'll do a dequeue. And looks good. All right, so right, dashes indicate nothing there. State 2, enqueuing. State 3, we're enqueuing. In state 4, we dequeue. Right, so our front of our list over here, and the back keeps on growing, right? So depending on how you want to look at it, our back, oops, is over here. It's over there, and then carrying on. The next time we insert, we'll insert at position 3. And go ahead and do some more operations. Enqueue 6, we'll dequeue, and we'll enqueue 2. Okay, try that again. Right, so enqueuing. Happens at the back, right? So we had our back here. Guess I forgot to copy that along. And we enqueue 6. All right, so now the back of the list is going to wrap around over here to 0, right? There's still space in the queue, There's only 3 data points in our queue, so we still have room for more data in our queue. Go ahead and dequeue. The front moves over to 1, and we now have space still at the back, and we're going to go ahead and queue. Back moves over, front's here, and we still have space at the back of the line. All right, so as we keep on dequeuing, front will do the same thing. Let's go ahead and a few dequeues. State 8. Back's unchanged. That spot's now empty, and our front is over here at 6. And state 9, back's unchanged. And the front is back. To the first index. So our next dequeue operation will be back to pulling 2 out. All right, we've had 4 dequeues on our array that has 4 elements. All right, so the front should be back to its initial state representing the front element of our array. Questions about queues at the moment? Sort, that's early. Okay. Let's see. Looks like a good time to take a break. So let's go and take 5 minutes. And we will swing back and look at some more code, talk about some of our labs we've been working on here. So, going on mute, we'll be back in 5. Go ahead and resume. There you go. Thank you. Okay, so we have a few labs and exercises people have been working on. All right, so dynamic arrays, let's talk about this one. Let's see, where's my main? That's not what I want. Yep. No, that's where I want to be. Okay. All right, int size equals 10. We'll pretend the user typed that in. And some people are trying to do this type of thing and then moving along. All right, moving along. All right, so Visual Studio flat out does not support this because it's not a constant in the version of C++, ANSI level, whatever, that we're using here does not allow some languages, some compilers, right, like our online is no problem with the syntax. Like, it's fine, we can do this. Wrong shortcut sequence. Now you want to create an array using this, that's fine, but this is not a dynamically allocated array. So for the compilers that support this, this is a stack allocated array. This, if we look at memory addresses, I don't know what the syntax is. Top of my head, I'm too busy working in C. Memory address we're going to find here will be a similar memory address as size itself because it's all in the same stack frame. Things can get a little bit sticky in how this implemented, or whatever it is, this is not dynamically allocated. All right, so to make this dynamically allocated, talking about the heap, and the heap means dealing with pointers. All right, via the new keywords now, we're dynamically allocated. Right, our array variables, our local variable, our stack allocated variable, tracking and memory address, that's allocated on the heap. All right, so when you're talking about dynamic memory allocation, we're talking about using the heap. Dynamic is one of those words that's has multiple meanings, right? So sometimes you'll say like, that's a dynamic data structure, meaning it can resize itself, right? Like a linked list, some people will call that just a dynamic data structure because its size is however big it needs to be. All right, so that's a separate concept as opposed to dynamic memory allocation. All right, so the key thing for this lab is the new keyword, because we're going to be using the new keyword all semester long. All the code that we're writing, we're going to be using new all the time, because you can't just stack allocate nodes and add those to a linked list, because those nodes disappear as soon as that function disappears. Right? We need the nodes to live longer than the stack frames that came when they were brought into existence, because those stack frames are transitory. They're short-lived, whereas the heap is long-lived. The heap lives as long as the application stays in memory, which is as long as we're going to need anything to live around for. All right, simple arrays, nothing special there. Array-based stack, all right, we just saw some of this code tonight. We need to swing back and take a look at anything here again. All right, it's pretty much one key line there and one key line here. If you're throwing exceptions, that's cool. If you're not throwing exceptions, that's cool, right? However you want to handle negative cases is not particularly important for this course, right? We're not doing application development here. We're doing data structure development and algorithm development. What matters is the algorithm is logically correct, it handling white space correctly or bad user input correctly, handles exceptions, all the things you want a real application to do are outside of our focus here. We don't care about overflowing the stack with an array-based lab, right? So if you didn't do any of this type of stuff, you just overflow it, that's fine, doesn't matter. The key thing is it's constant time operations. Doesn't matter how full the stack is, how big the stack is. It takes the same amount of time to add the millionth item to the stack as it does the 5th item to the stack, as far as the number of operations are concerned to get us to that point, right? So we're not talking about how many milliseconds it takes things to happen in, it's how many operations it takes things to happen in. Am I looping, right? Am I repeating the same operation over and over again? I less than n, I less than n, I less than n, I plus plus in a repeated fashion, right? That means more work to get there. Or are we doing direct random access? Right? This is one of the nice things about arrays. You have random access. If I want to get to the first element or the last element, it's just the same calculation and it gets us there in the same number of operations. IO lab. All right, I pointed you to string. Some of you are still working on this. And of the ones I've graded so far, I've probably had about 5 different approaches for slicing this onion. Some of you are building up your own. So let's do some different ways that we can slice this. Too many windows open here. Too many. What would I change? I don't need those. Hope I didn't break anything in there. Terrible named code file. That's why. Main. That way I can find it easier. Okay. Right. Splitting apart data. Right. So with C, we have two different ways of doing things. Right. You have C style strings. What are you complaining about? That's right. I have a CPP extension here. Rules change. Rules change. Okay. Let me back step for a second. And we'll go C style here. All right, it's fun, stirtoke. Oh, I guess I need my string library. Right, some library function to tokenize our data. Right, so this is extremely rudimentary. Not a valid Win32 application. That's fun. What do I have here? Wrong starter project. Okay. Build errors. This is terrible. Oh. Fine, fine. Da, 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 da. Apparently typing is rough for me tonight. Okay. All right. Let's go online because my brain apparently is taking a mental vacation. And see, it's been all 2 weeks since I taught the class. So apparently I decided to discard all of my C knowledge. See if I can't make the world happy here. There's two ways C strings. I could do angle. Of course, it's unavailable. Okay. Well, the point is, assuming this code wants to work with me, right? You could do sentence, right? Well, we can do it that way. Doesn't really change much on how we're doing with the C string. My resources are not going to be working with me, but we can go that way. See if we can get Visual Studio happy. Whom is my unresolved? Must be an L value. Anyways, this example has gone terribly awry, terribly awry. So let me go to get my code. Since the train got Big time derailed. And strings, string stream. All right, lots of ways to split the onion. So let's take a look at a couple of these. All right, so several of you found different ways of doing this, right? So ASCII to float. Still relying on the string stream to split. So what I was trying to demonstrate without success was different ways to break apart your sentences. Right, one way to break things apart is stirtoq. Break things apart looking for a delimiter. String stream is the same idea. It's a mechanism to break apart our sentences. And if we don't want to use the library function, here, let's go this way. Do a buffer. And we can manually split things apart. Well, sentence sub index not 0. We'll go ahead and break things apart. Buffer and let me add it to here. Right, some people are taking this approach of manually splitting things apart. Breaking things apart. And if IntelliSense does not want to work with me. If we come across the blank character, we can go ahead and spit things out. Sort of thing here. All right, back to C++. Okay. Using. No, gotta change my extension. I thought my spelling was truly failing me big time here for a second there. Probably have some bugs here, but not resetting my buffer index, but we got the hello. There's a bunch of garbage there. And then we got world, bunch of garbage there. And then we've got our number here. All right, so there's different ways that we can even just slice. Yeah, debugging, writing. I have to apologize. My day-to-day language is C#. So when I flop over to doing the C# example, things will be a lot smoother because I keep trying to type C# left and right all over the place here. Right, so our algorithm, we have to break apart our sentence, right? That's step one to our algorithm is break things apart. So stirtoq, manually doing it, looking for a space character, string stream, all of these are doing the same thing. That's the first step of our algorithm is to break it into a smaller piece. And once we get that smaller piece, we need to do it the second part of our algorithm, which is to transform it, or at least attempt to transform it into its numeric equivalent. All right. One of the ways we can do this, which some of you did, is with the extraction operator. Or the extraction operator on string stream is overloaded, so you can go ahead and create another string stream from the string that we created, and then try to use the extraction operator onto a float or double. And if it's successful, that means the sequence of ASCII or Unicode characters depending on which library you're using, is a number. Another way we could do this, ASCII to float, right? This one, right? Same idea. 5, -5, happy. Right? It identifies things as being operands, a negative operand, however you want to deal with things here. But it accounts for things if the number is less than 0, recognize negative numbers. Right? It's one of the things that some of your manual parser solutions had that I commented on was that negative sign. Or watch out for negative numbers because your parsers weren't accounting for that. And program 1 is a calculator. And that calculator can well accept negative numbers. So you have to be careful for that. Right. So ASCII to float, if this is a float representation of characters, including negatives, right? Negative 0 through 9s and dots. It's going to pull it out. If it fails, it's just going to be set to 0. All right. 0 means it's not numeric or it was 0. Either way, for our lab, we're still good to go. But string stream is going to be your better solution. For getting the data points out. Right, and this is one of the things where various languages are going to get you various mileage. Right, the way we would approach this with C#. Okay. And whatever, hello world, answer 0.5 days ago, split. Type fun stuff. Let's see, too many parentheses. Whatever. Right, land, double times 2 type thing. Otherwise, our word. Yeah, memory must be missing. Okay, wrong. Let's see. All right, different languages, different ways to slice the pie. All right, so depending on your language, this can get really short. So those of you using multiple strings, it gets pretty close. All right, to 4 lines of code like we have here. Once we actually get the data from the user. And the point is string manipulation is often one of the areas of software development that's not well taught in college because every language has its own way to bake the egg. And gets a little bit redundant when you're trying to learn languages to keep teaching the same concept over and over again in multiple languages. So this is why we have this as a lab, because you're going to be using your lab code in several of the programming assignments. So you want to make sure you're getting a handle on splitting strings, because strings are heavily and overly used in the wild out there. If I were to search our main solution of 100 whatever projects, and just for that string keyword, I'm sure I probably get thousands of tens of thousands, if not hundreds of thousands of hits where we're just using the string data type. Right? Strings are flexible. Numbers, addresses, telephone numbers, arbitrary data, JSON, XML, all that's often stored as string. So a lot of people will struggle with IOLab because it's not something that you always get in your programming classes. That's why I throw it at you early so you can try to figure out how to slice the onion up. So here for this lab, I really don't care how you're slicing it up. If you're using string stream, if you're using Sturtok, if you got your own implementation for slicing things up, totally doesn't matter. We're talking about just a mechanism to get the data from the user so that we can take that data and then use it in the construction of our data structure. Everyone sort of with me there? All right, so feel free to post code for the IOLab so we can get you through this one, because so as soon as we start working on program 1, you're going to want to take that your lab code and bake it in to get input from the user. Okay. All right, linear search, you've seen the code for this one. It's in the notes. The binary search. All right, binary search codes in Canvas, but we want to go ahead and write from scratch. Array size and whatever we're looking for. Right, what we need to do is figure out the middle. And we need to keep on looping as we move along, moving our boundaries as we get there. All right, so 2 ways that we can get out of this function. Either we're going to fail to find what we're looking for. How much C# should you expect in this class? None. That was just like when I did my little C tangent and C# tangent. That was just to point out that different languages have different approaches for the same problem at times. And that's the end of C and C# code references in this class. All right, so one exit case, we're going to have our code logic cause left and right to cross over each other to indicate what we're looking for can't be found. And alternatively, we find what we're looking for. So the middle is calculated by adding the 2 ends together. All right, so let's get an array. 5 elements, 2, 5, 8, 12, 14. All right, so when we call our binary search with our array, which has 5 elements, and say we're looking for 2. Five is our element size of our array. 2 is the key we're looking for, which happens to be our first element. So our left is 0, our right is 4, the last addressable index in our array, 14. All right, 0 plus 4 divided by 2 is 2, meaning 8 is the first element that we're going to look at. So we have a few cases here. If that element is what we're looking for. We found one of our exit cases. Should go ahead and return back that index. Otherwise, if what we're looking for is less than the middle value, then we want to look left. All right, so we're going to eliminate eight, which is that middle, presently 2, and everything to the right of it. So right goes from 4 to 1, representing the 2 to 5 range. And alternatively, same thing on the other side, where we set the left, equal to middle, plus 1. So if we weren't looking for 2, say we're looking for 14, right? We didn't match the value, it wasn't less than, so therefore it's greater than. So we're going to eliminate 8. Right, that's where our plus 1 minus 1 comes. It eliminates that particular value, and then everything that's beyond it. All right, so assuming I don't have any bugs in my code here, we should get out 0. All right, as where 2 is inside the array. All right, so if we want to do a little bit better testing here, just have it loop through everything. I less than 5, and we just go ahead and call our binary search on each element of our array. All right, we found it at 0, 1, 2, 3, and 4. Some negative testing would of course be appropriate. Want to make sure that something that isn't in the array isn't found, right? It's always good to test values as they would be expected to occur at different points in the array. Oops. That's supposed to be a copy. To make sure that there aren't any weird bugs working through our data stream here. And then we should get a bunch of negative 1s at the end for however many times we couldn't find the data we're looking for. All right, so calculating our own notation for something like this. A little bit more complicated. This part's easy, right? Assignment, 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 and a subtraction. This section is always constant. Doesn't matter if the array has 5 elements or 5 million elements. These calculations are the same. Same thing here in line 24, this calculation is the same. If we get to it, there's just one thing to do. It's the same as line 17. If we ever get to this line, it is a terminating statement, right? That's a jump statement that causes us to leave our function. Otherwise, the remaining amount of work that is to be processed is being controlled at a couple points here. The first point is where we're calculating the middle, right? We're cutting the array in half, right? Cutting the array in half is what gives us this nice logarithmic time. And here's making that array cutting actually practical. All right, so this divide by 2, it's reducing the problem set size by a fractional amount. That gives us our logarithmic growth rate. And if the code isn't being obvious, sometimes just some empirical testing. And every time we iterate, we can go ahead and just do some metrics there. Right, just have it return back as an out parameter or whatever we want to do. How many times is looping to get to the solution? And we just keep increasing our array size and then see what the growth rate looks like. Right, our linked lists. It's just like the code we're looking at earlier. All we care about is just adding it to the front and then printing out the list here. So just little subsections of the SSL code that we have in Canvas. Any questions about those exercises or labs at the moment? Some of them should have been fairly easy, not taking a long time, up to significant time for that IO lab, depending on how much you already knew. Yeah, you can share you want to share your lab code or exercise code on Discord, that's perfectly fine. That area is definitely collaborative. Right? You can work with each other, see how people are approaching things. If you're just copying and pasting their code, you're not getting any value out of it, or you're nowhere getting near the value you could get from it. It's much better to type. And yes, pasting as a screenshot encourages people to type it. And if they want to implement themselves, they at least, if they're going to look at the image, at least have to type it themselves to get their stuff. Yeah, so you're using a vector to store the words, which is fine. We're not using the word after we decide on it, so long-term storage or longer-term storage isn't necessary for the purposes of the lab. But it does give you a nice, separation of things. One step does the job of the splitting, and then the other step of the job can be self-contained in its own function, which from a application development standpoint is a nicer way to approach things. Now we don't have to worry about how you got your array of strings. You leave that work to someone else. You just know your job is to analyze the array of strings to see what's numeric and what's not numeric. Okay, let's take a look. At our practice test. Right, talked about that one already, so let's sleep through. Right, binary search. All right, so here you do have to do a little bit of math. 0 plus 7 is 3. So our first iteration, we're looking at 46. It's not 70. So now we're looking at this part of the array from 4 to 7. 4 plus 7 is 11 divided by 2 is a 5. All right, so our second test is 57. Now we're looking at here 6 and 7. 6, 7 divided by 2 is 6. Third test, and then finally a fourth test to find 40. Big O notation, adding a value to a link-based queue, right? NQ is big O1. Implement this code, find last. Right, so for it equals size minus 1, background equals 0, minus minus. Several ways to implement this. Doesn't matter necessarily which way you did it. This O notation is going to be linear at the end. And if numbers I is equal to our key, turn back I. All right, another common implementation for this might be the standard approach of starting at the beginning. And then the body's the same. It's just not as efficient. All right, since it is asking for the last occurrence of a key, starting at the end of the array is a better way to go, right? So say our array is 1, 1, 1, 1, 1, 2, whatever, 1, 1, 1, 1. All right, and we're looking for 1. All right, this is the last occurrence of 1. Start at the beginning. Oh, found it, found it, found it, found it. That's not it. Found it, found it. There, that's the last one. Right, if we start at the beginning, oops. I might have a little bug here. Index equals I. And index equals -1. There we go. Fix my bug. All right, this one just keeps on rolling because even though we find what we're looking for at the first position, we don't know that's the last one. So we have to keep looking, keep looking, keep looking until we get to the end. If we start at the end, all right, and let's say we have a 3 at the end, and we're looking for 1. The last element is not 1. So we can go ahead and go down 1. We get a match. That's our last element, and we can bail out. We don't have to look at the whole array. So we can improve our best case and average case scenarios here because we can get out earlier. Whereas this one, while it also works and has the same O notation, they're both linear. The practical work here is going to be greater than the first solution. All right, what's the front? So we have 10, then 5, DQ 10 leaves us 5, 17, 6. All right, so 5 is at the beginning of the list. And some of the tests will be like the practice where it's auto-graded. Right, multiple choice are auto-graded. Numeric answers should be auto-graded. This one would be waiting for me to look at your code manually and then see if it's close enough to what we're expecting. And if it's not, what the partial credit value of it would be. The other ways we can ask questions are multiple answer questions, in which case you'll get a square box here, in which case 1 or more might be the correct answer. All right, so let me find my annotate. There. So my Q states is 10, 10, 5, DQ, so my Q state's 5, then it's 5, 17, 5, 17, and 6. All right, so the front of the queue was 10, the front of the queue became 5, and that doesn't change until we DQ again. Oh, how many questions? Let's see, let me go ahead and pause. See how big. It was the last semester. All right. Test 1 has 18 questions last time I gave it, so 17 to 21 questions would be about the range of questions. How do you study for the tests? I recommend hitting the notes in the Google Drive, right? Making sure you're doing the reading in the book. Some of the things I only mention briefly, but the book goes into greater detail. And doing the labs and exercises are the best place to go for being prepared for the code writing questions. All right, when test 1's going to be still needs to be confirmed. Where is it? Do I even have it on here? There's the practice. Okay. Where are my tests? All right, it was supposed to be next week. Next week is a holiday, so it's not next week. So it'll probably just be the Monday after. I will post all the topics for that later tonight. So you have a full list of things to go through, right? Things we talked about tonight, things we talked about last week. Primarily focused on O notation, stacks, queues, linear search, binary search. Correct. We don't have class next Monday. We still have school during that week, so there's still labs and reading and stuff like that. We just won't be meeting and advancing the lecture part of the course. But yeah, there's all right. So let's see. Queues. Okay. Let me take a look at something, make sure I'm not. Anything? Yeah, so the 13th should be when the test is. Yes, let's see, ordered arrays. We need to talk about ordered, not ordered arrays and ordered lists still. Stacks, queues. And doubly linked list. All right. So let's see, 1.9. All right, ordered lists. All right, so ordering is a bit of a generic term. Ordering can be done in different ways, right? Stacks and queues are ordered structures. The stack is maintaining in a Philo order. Queues are maintaining data in a FIFO order. Another way you can order data is by sorting it, which we typically presume ascending order for the sort. Right, so maintaining an ordered list, we're talking about an ascending sort, means we need to pay attention to the data as it's being added to the list. Right, and the list may be implemented as an array or a linked list. All right, so when we're talking about list or set or collection, those are all synonymous terms, just represent a group of data. All right, so if I say list, don't necessarily presume linked list, because it may not necessarily be a linked list. All right, so our sorted array. Go ahead and add data. Following order. 5, 15, 7, 4, 22, 18, and 2. So my need for more columns are 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. Couple more. Column, column, column. All right. Index and states. All right. So our initial state, we had 5. That's our list. It's sorted. By definition, a list of data that has one data element in it is going to be sorted because there's no other possible arrangement that that data can have. Then we go ahead and add 15. 15 is greater than 5, so we just go ahead and tack it on to the end here. And we are sorted. Adding 7 is going to require us to shift 15 over to make room for 7 to go into its proper position. All right, 4 comes along, same story, but more shifting. 3 values get pushed aside. State 4, 22, didn't have to shift anyone around. State 5, 18 is being added, not as much shifting required. And then state 6, the whole wheelhouse being moved to make room for our data. All right, to maintaining a sorted linked list, it's still going to have the same idea. I'm going to simplify my box structure here a little bit, where we just have the right boundary, our link. All right, so let me go ahead and grab my data. All right, so our first state, we have 5, and that's our name node, head of the list, alpha, lowest, whatever we want to call it. It's our named pointer. All right, next data point comes along. That data point is greater than 5, so we should go ahead and link that on. After lowest, and let's move my name pointer over here to the side. Free up some space a little bit. As more data comes along, more nodes will be needed. All right, so we come along, create our 7 node, bridge the gap. The 7 node will link to 15, and then the 5 node links to 7. And not a whole lot. No. Still not a whole lot to do here, just a little bit more complicated because we are maintaining pointers and all good stuff, but some things are actually a little bit easier here. adding a small value instead of shifting a bunch of nodes here, right? We're not shifting nodes around. We're just resetting pointers to point to different nodes as space needs to be made. Right, so 22 comes along. Tag that on the end. Like we had before, we do have to do some shifting here. Move things around a little bit. Rearrange my white space. Things fit a little better. Okay. The fundamental problem we have with both our array-based implementation and our link-based implementation is getting to the point where we're going to be changing things. All right, so when we're adding 18 here into our list, right, look at our lowest value. That's 4, right? 18 is greater than 4, all right. What's the next value? Well, the value after 4 is 5. Well, 18 is greater than 5. All right, what's the next value? 7. This case still greater. 15 still greater. 22. All right, so we're looking at 22. 18 is not greater than 22, so we want 18 to exist before 22 in this data set. So what we want to do is to create a node that's going to sit in front of 22, set 18 to its value. We will link it to 22, and then we'll link the node that was left of 22 into the list. Right, so we have to iterate to that point to figure out where we need to change the links. Sometimes we won't have to iterate very far, right? Like in our last insert here, when we add 2, I looked at lowest, saw the value 4, and I said I'm trying to add 2. And since 2 is less than lowest, create the node, link it to 4, and I update this new node to be lowest. And we're done. So what's the worst case for our array implementation? When I wanted to add 2 here, that meant shifting everyone down the line. Was actually our best case over here with our list linked based implementation, where the smallest value was already in a good spot. All I had to do was set our links. But our implementation here is going to be linear. Every data point we add, right? So our array-based implementation, worst case scenario, everyone has to shift over to make space for a new value that's now the smallest. Or with our link-based implementation, worst case, we're adding a largest value. I have to iterate all the way down to the end and then add that value to the end. Some implementations with a link-based list, they'll actually add a tail pointer, so we can go ahead and take a quick peek at the tail. Because sometimes when we're building a list of data, it's already sorted or partially sorted, and we're adding 1, 2, 3, 4, 5 to the list. So we can get a significant gain in performance by looking at the end to see if the value we're adding is greater than the last element, because if it is, adding the tail is very, very easy if we have a tail pointer already there, because that becomes a constant time. So what is the cost of adding a single data point when array-based? Right, so worst case analysis, all data points are shifted over to make space. Yes, we have a linear problem. Right, same question, link-based. Right, so our worst case analysis, have to iterate towards the end of the list for setting pointers. And even with that optimization, it might be 1 before the last node. So we're still close enough to our worst case. If we have 1,000,000 elements in the list, the new value might be 1 less than the largest value, which means I'm going to have to iterate from the first pointer all the way down to, that's an excellent question, Arthur. I'll get to that in a second, all the way down. So like 18, right? So I want to add 20 here. I have to iterate all the way to 18 and see that 22 is bigger, and then manipulate our pointers. So can we use binary search here? Yes, we could use binary search on our sorted array to help us find where we want to get to it. Once we've found that position, we still have the shift problem. So the binary search can help optimize that a little bit, because we're adding to the end. We can skip all that fun iteration to adding to the end. If we're adding to the middle, we can skip all that iteration to adding to the middle, but we still have to shift a bunch of data elements. So yes, we can improve that other aspect of getting to our insertion point with the array based. So yes, you definitely can use binary search. And if you look at the library implementation of binary search for the C standard library, it actually returns, I think it's C standard, it might be in my .NET C standard library is confused. But it should return back the 2's complement, which if it doesn't find the value, it tells you the index of where it wanted the value to be. So even if we can't use a library binary search, we can still use a binary search algorithm to give us the jump to the insertion point faster, and then shift down to it. So we'll know where it is, and then we can shift. It's actually easier to shift from the end than it is from the middle. When we get into our sorts, I'll show you how that works. But knowing where the insertion point is with a binary search does help optimize a little bit. All right, so building an ordered list from scratch, which means building a list of n elements where each addition is big O n means the total cost is big O n times n, or n squared. Good old quadratic O notation for creating and maintaining an ordered list. So it's a little bit of an expensive thing here. But as was asked, the binary search is supported. So if we know we're building numbers and we want to be able to search for it as things are coming in, we're well suited for the sorted array to be a good implementation for maintaining a sorted list. Right? The drawbacks that we have with arrays is when they're made originally, they are fixed in size. So that's a little bit. But all problems have solutions, it's just a matter of what the cost to that solution is. Is there a reason not to use binary search? Since we're going to be shifting everything, one could argue that we're just going to be starting at the end and then moving the values. So instead of finding where it goes, we're just going to move the whole to the position, right? Where we take this approach, let's say, right, we wanted to add, let's get the values. Right, we want to add 1 here, right? So the first thing we do is we move 22 over here, which I don't have a space, so I'll just leave it blank because we need to make space. Then 18 moves over here, then 15 moves over, and then 7 moves over, right? So we just start off, we skip ahead to the shift step. then we can insert things in. Right, so actually finding where we need to insert the data point isn't necessarily how we would implement the code. Since we know a shifting operation is most likely, even if we need to add 99 at this point, we just jump to the end, 99. Oh, already greater than the last data point, so we're done. Right, so we're actually, the implementation will actually skip ahead in the algorithm to the shift step to make space for where the data point's going to go. So we're just shifting until we have this, the hole where it needs to be, and then we're done. But yeah, the concept of using binary search here is a good thought experiment for how we can try to improve the implementation of the algorithm, right? Because logically we need to find where it goes and then make space. Implementation wise, we can flip it on its head and go ahead and make the space, which also in turn finds where it needs to go, right? Because a shift, right? Shifting pseudocode, right? So basically, while I is greater than or equal to 0, and array sub I is, let's see, greater than the data, we just go ahead and move the value over. I plus 1 equals array sub I. All right, so this copies the data over and makes the whole, and then we can go ahead and set array sub I equals the data. All right, so this is basically the code that we need to do to insert the data point, where I would be initialized to the last element, next element, something along those lines. I gotta make sure we don't clobber in the existing data point. But that's more or less the code that we have to shift things into place. Okay. Doubly linked lists. Double check that this is, give me the proper sorter. Good, all right. All right, so doubly linked list means our node structure has two self-referential pointers. Commonly, one pointer points to the next node that has the next value in ascending order. And the other pointer points to the node that has a value lower than the current node. All right, so start off a little bit generic, where we're not presuming any order in the data. We just have two arrows, one referring to whoever's next, and then one who's referring to last, previous, however you want to call them. All right, so there's data one, whatever the data is. And when we have a doubly linked list, we're more commonly going to have both ahead and tail node. All right, so this is the list, single node list. And when we add to the list, right, it might go either way where we're adding to the tail. Right, so it's just be an add to tail situation. We'll link the existing node to our new data point, and our new node links back. All right, so we just have forward, backwards, so we can start at the end and work our way to the front. We can start the front, work our way to the end. Or move forward and backwards if we need to. Okay. Big text boxes. All right, data point 3. Whatever its value is, arbitrary. It would become the tail. Just like we did in the previous edition. Same idea, add to head, just like we have a single linked list. All right, except we're just adding in front of our existing data point. And the head is the one that's changing. There's just more pointers to concern ourselves with. Like before, first step, create the box, set its data, and we want to go ahead and set its first pointer, if necessary, to one of the other nodes in the list, and set its second pointer, if necessary, to one of the nodes in the list. All right, add to head, to tail, not a whole lot changes because adding to head, that one pointer will be null, and add to tail, one pointer is null, so it's just setting one extra pointer. When we're talking about adding to the middle, this is where it's a little bit more involved. All right, so let's add to middle here. So we had data 2 and data 1, and we want to add this new data to the middle. All right, so our initial state, right, data 2 points to data 1, so this pointer, instead of pointing to data 1, is going to have to point here, and we had data 1 pointing to data 2, so this pointer here. All right, let me see if we change some colors here. Where's my light colors? That pointer changes, that pointer changes. And these two are new pointers. Just color those red. They need to be initialized. All right, so just like adding to the middle of a single linked list, we're going to need to iterate down, get a temp pointer that is representing either the node on the left or the right, from which we're going to start bridging this gap and putting a new block in between. We want to set the red pointers first. The order doesn't matter. We can set our new node to data 1 and set our new node's other pointer to data 2. Those orders are interchangeable, and the same thing here. These two green pointers need to be updated. So depending on which one we're bridging from, if we're bridging from data 2, we can link to data 1 still via the original pointer state, and then set the back pointer, and then from data 2 set the next pointer to the new node. And it's pointer maintenance. So we got to make sure our pointers are pointing to the correct thing. As you're trying to craft code for linked lists or trees or any of the linked structures, I highly recommend a pencil and paper. Draw out what the list should be. That way, when you're trying to step through your code, you're on data point 2 as the head of the list, and you're looking at your paper, you're on data point 2, things are lining up where things are. Because since we have an abstraction layer and then we have a code layer in between us and the actual data, it can be very, very easy to get lost to where we are with things. So I recommend just draw out the lists on pencil and paper and then step through the code and try to track and see where the temp pointer is. Is the temp pointer over here on data point 2? Is the temp pointer on data point 1? That's more or less the idea. Right? And deleting, it's the same idea as deleting from a single linked list. It's just more pointers to clean up. Right? If we're collapsing the bridge, same thing, same steps, just additional pointers that we need to worry about. Okay, let's go ahead and take a 5-minute break, and then we will look at some more code for this. I wasn't thinking ahead. Doubly linked. All right, so we have an addition to our doubly linked node, right? So we have 2 links now, plus the 1 data point. So we add the last pointer up to update the constructor to have last pointer logic. Otherwise, it's very, very similar to our singly linked list node. Right, still the same 2 named members as we had with the other sample code, a head and a tail. Constructor, same thread. Deconstructor, right? So skipped over SLL1. We'll go ahead and dig in here. So we just go ahead and create a temporary pointer. And so long as the list is not empty, we're going to go ahead and set our temporary pointer to the next pointer of head. Delete the head, and then the head slides down to our temporary pointer. All right, so we have 5 boxes in our chain. Head's first box. Go ahead and set our temporary pointer to 1 past it, so it's box 2. Delete box 1. Give it back to the system, and then head now is pointing to box 2. Set our temporary to box 3. Delete box 2. Point to box 3. P points to box 4, delete box 3, and it keeps on going until P ends up being null and head ends up being null. And then this is no longer an empty list. Is empty, same. Add to head, right? Very, very similar to our other add to head that we've seen. Key difference being here, add an extra parameter here for the last pointer or the previous pointer. Right? It's going to set the previous pointer to null when we create our node. All right, so straight out setting it to the head, set it to temp. And we'll look to see if the head isn't null, right? So it's important null check so this doesn't blow up. Otherwise, the very first insert causes code to blow up. So if the list is not empty, the existing head is going to point to our newly created node. And then we set the head to our newly created node. And like before, if the list was empty, the tail and the head are the same node. Add to tail. Here's where we get our improvement. With our singly linked list, add to tail required a loop, no loop. Since we have that back pointer, we can immediately start at the tail and start doing our work, right? So the same As before, we need to create a box with whatever data point is. That box is going to point to our existing tail. All right, so second parameter is point to existing tail. We didn't pass the third argument, so our next pointer points to null. And that is our temporary pointer pointing to that box. Our existing tail points to the new node. And we slide the tail back down. All right. Otherwise, we have similar cases we had before. The head and the tail are our newly created node. All right, deleting from head. Same precondition as we saw before. List needs to be non-empty, otherwise this is a null reference exception. Temporary node to clean up memory like we had before. We have the case as we had before, a single node list going to a 0 node list means head and tail are empty. Head equals head next, like we had before. And then our one addition is to not have a dangling pointer, right? Because this was pointing to the old head. So the new head needs to not point back to the old head anymore. And then delete from tail, similar idea. And I misspoke earlier. This is where we removed our loop. Same precondition like before. Watch out for those null reference exceptions, also known as the $1 billion mistake. You want an interesting read about the $1 billion mistake, right? It's talking about null references, right? I forget when they decided to start calling this a $1 billion mistake, but I'm pretty sure we're growing into the trillion range now because null reference exception is a very irritating bug, right? Not having data is inherently problematic. Anyways, our last pointer here, since we have this last pointer here, it saves us from having a loop to get to that previous node that exists right before the tail, because we can go ahead and slide the tail backwards. And this extra pointer means we don't have to have a linear delete from tail situation, which is going to be a driving reason why we would bother with two links. And so if we know deleting from the tail of the list is an operation that is going to happen on some sort of regular basis, then we want to move from a singly linked list structure to a doubly linked list structure because we can improve that operation. When we're trying to decide what is the appropriate data structure to use, we need to fully understand the problem that we're trying to solve, and in particular, which operations that we're going to be doing on a frequent basis when solving our problem. Are we adding to the list often? Are we deleting from the list often? Which end of the list are we often adding to, or which end of the list are we often removing from? Can change which data structure we want to work with, right? So just like stack or a queue, right? What's the order of the data nature, or how do we want data to be persisted? Do we want that FILO or do we want that FIFO? Because that drives what the implementation needs to be. Going back to the queue example, are we just doing standard queue operations where no one can jump out of the line, no one can cut in the line? We're always adding to the end and we're always pulling from the front, in which case it's a single linked list is still going to be good, but now if we have a need to allow for people to leave the line, and often people who are going to leave the line are the ones that are most likely towards the end because they haven't got as much time committed to the endeavor. Right? People at the front of the line rarely are going to say, oh, forget about it. I don't want to watch this movie anymore because I've been waiting for half an hour. Or I don't want to pay for these groceries. I'm just going to leave the store because I've been waiting half an hour. Right? Sometimes it happens if you're on a tight time crunch, you might bail out of the line when you're at the beginning, but you've collected all your items in your cart, and you go to the line, you see it's very long, and class starts in 2 minutes. Sometimes you have to bail out even though you just got in. So you first have to understand what operations you need to support, and then which operations are more common, because there's cost. If we're by adding in these extra links, every time we add in a new data point, there's more links to set. Every time we remove a node from the list, there's more links to set type thing. So that adds a fixed overhead to all of our operations. Right? As we start looking at more algorithms and more data structures, keep talking about how to analyze version A versus version B of the same basic solution, or option X versus option Q for very different approaches at solving the same problem. Right, delete node. Once we get to the generic case, just more pointers to set. And the syntax can be a little bit interesting here, where we have our temp node, which points to a last node, which has a next node equals temp next. So just have to be careful with your timing of things. As pointers change, you have to be careful so that you don't run into bugs, right? You have to just watch your timing. This is where drawing things on the paper. See who your temp node is, see who you need to set next or last first to make sure things are lining up. Right, so the sorted doubling linked list will be a little bit more practical for that inserting and deleting in the generic case. Right, so it has everything folded in. Whichever way we go, we're creating the box. Sometimes it's an empty list, and that's all we have to do. Otherwise, we need to iterate to where we're going. Just start sliding down, as we've seen before, and then just do some extra tests to make sure we are accounting for the head and tail as needed, and setting our 4 pointers to get the bridge going. Right, as I head in our Google Doc, first manipulate the new node. The next pointer when we create a new node was null, so we can go ahead and overwrite the contents with no concerns. The last pointer was null when we create a new node, so we can overwrite it with no concerns of data loss. And then we go ahead and switch things around, right? So here's our case where our tail was where we're doing insert, and the similar idea here with temp. And this code could be reorganized to be a little bit shorter, because you can see we have similar code patterns in multiple places. But this one was trying to be as exploded as possible so you can see all the minor steps. Okay, brings us to a circular list, or circular linked list. Right, so a circular linked list is conceptually the same as our circular array, where the last node points back to the first node. So if we go ahead and create a node 5, whatever, it will link back to itself. As we add nodes, it actually starts to look more and more like a circle. Let's see, so let's say we add 22 next. Whatever it is somewhat arbitrary. And go straight there. As depending on where we're adding, we'll assume we're adding at the tail. Try that again. But the last node just swings on back to the beginning. Getting ahead of myself. All right. Right, 17 comes along. And just link it in, update the tail. Right, so if we had a job scheduler and the job just refers to one of these nodes, so that pointer can just keep on sliding around this list, and we don't have to do anything. If someone comes in, just add it into the list wherever we need to. We can just use the job pointer, just depend on what we're using this structure to implement. But the fundamental nature is whoever is the quote unquote last node, it links back to the first node, whoever that node is. And you might just use a single name pointer to track things. Doesn't much matter. Key thing is we never have a null pointer. Right? Pointer is always referring to someone with the exception of head and tail. Right? The list itself is empty. Right? The initial state, those are null. But the node pointers are never null. The next is always somebody, even if it has to be itself. So that can get a little bit tricky if you want to do like a print function that prints all the atoms out. Right? Our normal mechanism to stop the loop is when we get to a null pointer for next. Right? So we temp equals head, print temp equals temp next, and while temp is not null, just keep on printing temp next. Problem here is right, it wants to naturally just keep on spinning around in orbit. So we have to have something to tell it to stop its spin, because we don't want to keep on going forever. So one way to do that is we can leverage the name pointers. If we are always starting ahead, just as long as until we get to tail, then we can stop. Or we can do a temporary pointer, right? Temporary pointer equals 5 for where we started, and then start the looping. And while that looping pointer doesn't get back to temp, we can keep on going. Right? All problems always have solutions type thing. Okay, let's see, where are we? All right, so based queue, link-based stack, array-based queue, and sorted linked list. All right, so our link-based queue. Right, just like we saw with single linked list code, single linked list code would be your code template. If you're getting stuck that you want to refer to, make sure you're naming things appropriately, right? The method is called enqueue and dequeue, not add to tail and delete from head. Right, whatever you want to call your named nodes, that's somewhat arbitrary. If you want to call it A and B, first, last, oldest, newest, whatever. Do you remember that there is a new member here that's not in the code base? I need to add a count. This tracks how many items are in the queue. So every time you unqueue, the count goes up. Every time you dequeue, the count goes down. Otherwise, you've seen most of the code here. Any questions on our linked-based QLab? Link-based stack, same thing. You start from the same code base. Remove the parts that we don't need, or we don't need a tail. Stack does not care about the tail. Right, the node structure can be left alone. Push adds, pop removes. When we push, we increase the count. When we pop, we decrease the count. All right, key things to these two labs, just getting used to your pointer and new syntax, and then just setting your pointers. All right, once you get over that hurdle of what a node is, it's not terribly bad, but you know, if pointers are a foreign concept because you took Java as your primer for this class instead of C++, right? You have to put the star in there, and dots are arrows, but otherwise it's mostly the same. Now it's due dates are still in flex, and with Monday being a holiday, that flexibility will probably extend all the way till the 10th. Was it 7, 8, 9? Yeah, the 10th. All right, so it won't be until we get to the 10th that I'll probably even enforce anything on the due dates. Just as soon as you think you have an idea of what to do and time to do it, you know, take some shots at it, see if you hit the target. Array-based queue, right? So the key thing to this one is the array needs to be circular, right? The front and back wrap around. If your queue can cause itself to be full after doing a bunch of NQs and a bunch of DQs, then we have a problem, right? If you NQ 5 items, DQ 5 items, NQ 5 items, DQ 5 items, you should still be able to NQ 5 items, even if your array can only hold 10 elements, right? We've gone through 10 NQs and 10 DQs. The queue is empty. There's no reason why we shouldn't be able to accept more items into our queue. Do remember NQ and DQ are both big O1. These are constant time functions. Don't want to see any loops inside your structure code or class code. All right, so we're linked list. To this one, it's just a matter of making sure you're understanding which pointers to manipulate when adding somewhere in the middle, trying not to get lost on the head and or tail as you're adding things. And again, pretty much the code for most all this is in the file section. Linear structures being where most of this good stuff will be. Don't know why I still have a C# code file visible, but if you want to see how it's done C#, it's there. Questions? Which is the better method or more efficient method using a struct or a class? I would use classes. The whole purpose of a class is to allow you encapsulation of the data and then keeping the functionality tied to that data. Right? If you're using a struct, you're just doing global functions that just take a node or take a list as an argument. So you have to forcibly give it the context. Whereas with an object, the object uses itself as the context. Right? It's effectively the same thing. And for our class, either way is fine because we're not dealing with large applications, but trying to develop large applications using structs becomes very, very problematic because you have to try to keep the code organized, and classes are an inherent way of keeping code organized. But yeah, as far as data structures are concerned, it doesn't care that it's a struct holding on to a memory address versus a class holding on to a memory address. We're still newing up or mallocing the nodes anyways. Okay. Let's talk about testing code. Let's see where I can find. What labs? Okay, redirecting input. Why is this in programs? I guess I have some code in here. All right, so let's go and create a simple program. Test our stack. Let's see, do I have a reference here already? Okay. Not what I meant to do. Okay. Da, 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 da. All right, so we have our stack class that's inside the code we're looking at earlier. And say we want to write a program, whatever, that asks the user to do stuff. All right, enter 1, push. And let's do some red lines here. Two's pop. Let's make this indeterminate. 3 is exit. So our choice equal 3. All right, simple program just looks at our various options. Gets a number to push. And then pushes said number. I guess I should just print out the count. Do, 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 do. All right, case 2 is pretty much the same thing, except we're gonna pop. As blank items, we go and add popped, pooped. Same difference, right? All right, so we can test our code. User says to push. Let's see, where's my bug? See in number. Okay, let's see. It's 3 work, 3 work. That's fun. Bugs are always fun. That's what the debugger's for. See what I goofed up on. Oh, I didn't actually ask them for the choice. That would be a good idea. Excuse me 1 second. And I should probably prompt for the number. That's usually a nice thing to do. So the user's not confused at a blinking cursor. Okay. We're gonna push. We push 5. Stack has 0 items because I got a bug. We'll push a number. We'll push 12. Stack has 1 items, right? Because that bug's there. Get in a second. We pop 12. The stack has 0 items. We exit. All right. So I know I have a bug. So I gotta go fix the bug, test the code again. All kinds of fun stuff. So alternatively, if you go find where your executable is, let's see, where's my executable? Should be in here somewhere. There's my main. Am I hiding extensions? Am I hiding extensions? All right, exe, where is my fun executable? There we are. Right, it's an executable, means you can run it. Right, run it, double click, run the program, does whatever. Does whatever. All kinds of good stuff. So since it's an executable, you can go ahead and open up a command shell. I don't want PowerShell. I want a command shell. Let's keep it simple. All right, open up a command prompt. No, there isn't actually a count variable. We'll get to that in a second. I'll show you what the bug is. I'm working my way to it. But yeah, the bug is in my stack.h. Right, we can also run our program from the command shell, right? Do whatever, push things, exit. So we can also create test files. Right, so this is the Simpleman's unit test pattern, if you will. stack test 0, text file. And it's just going to work with my particular program because my program's a full program. It's a little bit of pain about 5, 1, 10. Push things out, and then we'll exit. Get there, get there, get there. All right, so we can actually feed input using little DOS command here. So we can redirect from the standard input this data file. So it actually runs through. They typed the 1, it has 0 items. They typed the 1, it has 1 item. They popped, they pulled 10 off, and then it exits the program. CN is white space. So this same time, I could have done white space here just to work. Right, we'll just go ahead and make a copy. So copy as. Do 1, and then do a little fun, find replace. This white space. And I guess I changed program 0, whatever, same difference. Right, program 0, same thing, right? CN's white space based. Just like scanf. Right, so this is fairly easy to do. You write your program, you know what your program is expecting the user to type at various points. So you just go ahead and create a test file. So when you go in and fix your bug, you rerun the test file and take a look at the output and say, okay, now the output is better without having to type it all over and over and over again. Now, if you want to be sophisticated, and, I'll post a link in the announcements. What you can do is what's known as unit tests. Unit tests is code that tests code. And so right now I actually have my tests are failing because there's a bug. All right, so here I have some test code. It creates my stack, right? So it's still using the same header file as it was over there. And it creates my stack and it tests things are lining up. And here we start to have bugs because my counts and things aren't quite equal. No, you don't need to give me test code. You just, for labs and exercises, or for labs, once you turn those in, yeah, just your code and a main that calls it is enough. Right, so it doesn't, you don't need a unit test, right? I mean, if it says exactly what the lab says to do, then you're good. Ideally, you have a main that's actually testing your code so you know your code works. But if you're that confident in your linear search, you don't have to write a main function, then that's fine as well. Yeah, this is Visual Studio. Right, so my tests failed, empty stack. Right, I expected to have 0 items in my stack, but it said there's actually -1 items in my stack. Right, so my code has a bug. The count is saying top -1. So my bug's here. So I can fix my bug, compile things, make sure everything's all happy going. And I can tell my tests to run again. And it's going to run through and do all the fun stuff and make sure that the code's good, right? Now my code's good. All my tests pass and done. Right, so there's another area where I'm trying to sprinkle in things at the end of the class during our lab periods, useful things that often are, you don't find out until you actually get your first job. It's like, whoa, I didn't learn anything in college, which isn't true. You just didn't learn everything you're going to need to learn. So this is way beyond the scope of this class. If you're caught up and up to date, I didn't create any namespaces I'll post the links to the article. It tells you, right, what I created. Right, so I created a library. So I'll show you. Let's go ahead and add new project and a static library. Right, so you can search library, static library. So the static library is where I have my stack code. So that's this particular project here. It's got my stack code. This is just generic blank stuff that came with, I didn't mess with. Generic blank stuff that came with, I didn't mess with it. And for a reason, I have to include this header file. I don't usually use C++ to do this myself. I'm using .NET. So the principle is the same. The little lines that you have to get in order is a little bit different. So I don't have all those fun details. And then this here is a unit test project. So right click the solution, add a new item. And this time it's a test project, right? Native unit test project. And then what we do over here is you add a reference to the code you want to test, and you just start updating the standard test code it gives you, and you just start cranking at it. Just write tests. Right, I even have a test here that looks for me trying to, remove from an empty stack or things that are not supported, and you can write more test code here. So if you're up to date on all your coursework for all your classes, this is an area that you should look into to further your understanding of things that you'll likely actually be doing when you're released into the wild. At some other point, we'll talk about source control. It's another critical thing for software development. And here and there, as time permits, we will swing into those other things, and then I'll try to bring in some real world examples. There's several times where I've had to develop solutions. Yeah, I'll do an announcement on Canvas for the link. I do C++ unit tests because I had to Google it all myself to put this all together, because it's not a native skill set doing this particular flavor of unit tests. Yeah, several times at various jobs I had, performance was not there, right? And that, again, this class, 97% of my development work isn't, the things aren't performant and we need to get in there and do it. But every so often we find that we have bottlenecks. Things are just moving too slow. And that's when you go do your deep dive and you start digging in and you start looking at O notations and figuring out, why is this thing slow, right? My most recent one was I had a back-end service processing these data files, and it was getting to the point where it was taking tens of minutes to hours just to get through one file for one company, and we had to do the same thing for multiple companies. So it was basically every week data was coming in, and it was taking it more than a week to get through that data. Right, so I have a little case study that I put together last semester for this, showing, right, the performance impacts of what worked well for probably 10 years, got to the point where it was no longer sustainable. The amount of data grew, and with the poor O notation, small growths start to add up into real time really quickly, where you just see a CPU burning away 24/7, trying to get the work done. Same thing with our data structures. Each data structure has its area of expertise, places where it works and places where it's just not relevant. Right? We're not going to be making queues for every other thing that we're developing. We're not going to be making trees for everything we're developing. We'll make trees very often, but there's going to be areas, and I'll bring up those areas where they're relevant, right? So just like job scheduling, right? Queues and priority queues are often going to be used for job scheduling problems. Stacks are used all the time, right? Or we have stack-based architecture for programs and function calls and the like. Okay, so that's it for lecture for tonight. Are there any other questions before we talk about time? All right, again, we have no class. Will I get into the loop unrolling? I'm not too sure what you mean by loop unrolling. There's stack unwinding for exceptions, which would be a no. There'd be unwinding the recursive chain, which we'll get to next time we meet when we start talking about recursion. How do we know how to learn the stuff colleges don't teach us? Well, that's trying to give you breadcrumbs to go chase down. When you take a software engineering course, you'll get a lot more of these again, but software engineering is such a broad concept that you don't get a lot of it. So there'll still be more breadcrumbs. All right, so I try to sprinkle them in here as little side things that are beyond the scope of the course, but are things that you want to apply your interest towards because they are very commonplace activities. Okay, let's see. Another way to try to jump ahead to try to figure out the things that you don't learn in college is to look at job postings, right? Because job postings will say, they want X years of experience or X or Y degree. And then you'll get to like the preferred section, prefer that right? JSON, XML, what do they call it? Bootstrap. There's common CSS and jQuery and things like that aren't languages, but they're tool sets built on top of a tech platform that are heavily used by the way that their tech stack that they decided to go with. So those are things that's okay, what is this? And start digging around. Right, things to come. We have sorting. Right, this needs to be moved. This date's very wrong. Right, talk about sorting. So sorting, I will post some links for reading things about what we talked about tonight, things that we're talking about in the near future, but sorting, there are several sort algorithms I'm going to go over. Bubble sort, selection sort, insertion sort, quick sort, and merge sort to start. And then recursion. You've probably seen recursion in one of your other classes. But here, as soon as we move beyond nonlinear, recursion becomes critical. Right? Trying to work code that are tree-based, which is a nonlinear structure without recursion, is just not gonna cut it. The code complexity goes up. Otherwise, we do have program 1. I'll direct you to some links here. I'll probably have to tweak the due date on this one because we're missing class on the Monday. But this is just implementing a link-based stack. So you're going to take your link-based lab for the stack, and we're going to put some practical use to it using reverse Polish. And reverse Polish is pretty easy. We get an operand, you push it. So you push 10, you push 15, you get an operator, you pop a couple of values, and then you just operate on them. All right, so I'll post some reading for you so you can check it out. But I'll probably push the date on that one to account for the holiday. So otherwise, we'll be talking about reverse Polish next time along with those other items. Yeah, binary search can be done recursively. Since it can also be done iteratively, iteratively will be faster. So you don't have to keep calling the same function over and over again. It should be faster. A little bit less overhead and less memory. Yeah. Well, just like learning how to code, the best way to learn how to code is to code. All right, just like riding a bike. Best way you can read about a bicycle, read about how wheels work, how the brakes work, all that good stuff. But until you get on it, it's not going to really click into place. Software development, same way. You have to do it to learn it, because reading about it and then taking that rubber to the road is where it starts to really leave a mark. All right, so the rest of the time is just break and lab. So if you're getting stuck on the labs, keep pinging me and we can help you out, right? So feel free to post lab code in Discord, message me lab code in Discord, Canvas, whatever, email. Again, Discord is your best turnaround time, right? Because I see a little icon in my taskbar that there are messages in Discord. I'll see that way more often than going into my mail client and saying, oh, I've got mail. Sometimes I go days between checking my mail, especially on the weekend. Have a good night. See you in 2 weeks. See you on Discord and watch your announcements. And keep on turning stuff in as you figure them out.